So 40 degrees is just shy of the original initial arm. And what's another way that we could get here? Now some people might say, let's just do a full 360 and add a 40. So you could say 400 degrees. Great answer. Another person might say, well, what if we went in the other direction and we did whatever 360 minus 40 is? Negative 320 degrees. Both of these, all three of these are called coterminal. I'll skip out the last one, but it's a very similar one, and we'll go on to coterminals in general form. Now, I did say that you could have multiple answers for the same terminal arm, and there is a mathematical way to represent all of them at once. Okay, so if a given angle has an infinite number of angles coterminal with it, one expression can represent all locations. So if we were to say 0, 360, or negative 360, if you go the other way, which is the same as 720 and so on, this is sort of being visualized by 0, 360, 720, and so on, or going the other direction. But what we want to be able to say is our angle is every multiple of 360. And how could we represent multiples? Well, I could just say every 360 degrees, times it by 1, times it by 2, times it by 3, times it by n. As long as n is an element of the integers. As long as n is a 1 or a 2 or a 3 or a 4 or a 5 or a 0 or a negative 1 or a negative 2, now I can say plug any number into n and it will be coterminal. It'll be on a 360 degree rotation. Now this is very similar in radians though. We're simply saying our angle could be a 2 pi, which is the same as 360, and then just put another n on top of it. And n is an element of the integers. So these are two ways to represent very, very perfect places of 0 degrees. As we flip it over, sometimes they can be a little bit more complex. Now, not crazy complex, but a little bit more. And what we've got for this try example on the next page says 150 degrees. So how can we say 150 in every full 360 that happens? Because we're saying 150 and then do a full rotation. Well, we can word that in almost the exact same English way in math. Start with a 150 and add a full rotation. But that rotation could happen once or twice or n number of times, as long as, again, n is an integer. Similarly for b, it's almost the exact same thing. Just take your 280 and add a full rotation. As long as n, again, is an element of the integers. It includes the positive direction and the negative direction. Well, good news, we're in the last part of today, and we're talking about the arc length of a circle. Now you might remember, and I'll just do this little visual on the left, that if I were to talk about the circumference of a circle, I would ask, what is it based on? And you might say it's r. The circumference of a circle is actually 2 pi r. And you didn't know it, but there's a very, very deep connection to that formula, and asking, well, what if I didn't want to talk about the entire distance around the circle? And that is actually called the arc length of a circle. Arc is like a curved surface, like talking about angular momentum in physics. We're talking about the arc length is a portion of the circumference. The arc length of a circle is a very nice formula where A is your arc. We'll call it our arc length. That angle is our central angle, and I will draw a little angle to represent our central angle. Important to know that this central angle needs to be in radians. If you plug in degrees, your value will not work out. And r represents the radius. So there really isn't a ton of things, but the most important thing to remember is that your angle needs to be in radians. So two questions to round things off. And I guess it makes sense that if we're talking about a central angle in a circle that's a full 360 degree central angle, it makes sense that your theta is 2 pi r. And everyone's jaws just dropped. 2 pi is 360, 2 pi r. Very, very beautiful. So in example 4, it asks to determine the arc length of a circle with a radius of 6.7 and a central angle of 130 degrees. So a quick visual. There's a circle. We have a central angle of 130 degrees. Also notice that my central angle is terrible. But there's 130 degrees, and there is a radius of 6.7. And we go into our arc length formula, which is arc length equals theta times r. And we just plug in our numbers. Our angle is 130 degrees. Although my pen either seems to have run out of ink, or I shouldn't write 130. Good catch. We needed to turn that 130 into radians. We'll do a little side math over here. Pi radians is 180 degrees. Fact. Line on top of each. Central angle is 130 degrees. Unknown radians is x. Cross multiply to get your x is 130 pi over 180. There's your central angle in radians. So 130 pi over 180. There's your central angle times your radius of 6.7 centimeters, which will stick with this. And so when we number crunch this in our calculator, we have a 130 pi divided by 180, enter, central angle times the 6.7, and 15.2 centimeters results. 15.2 centimeters is the arc length. The arc length is the distance between those two radii. That is your arc length. And maybe we'll visualize that in the definition above. The arc length is the portion of the circumference between those two radii. And in the very, very last example, it does say determine the central angle for the arc length and the radius. So rearranging our formula arc length is theta r. We can rearrange this so that theta is equal to an a over an r. Arc length divided by radius. Arc length is 13, radius is 5, and if you divide 13 divided by 5, it is 2.6, and the units are radians. A very strange number, but 2.6 is a little bit less than 3.14. It's a little bit less than pi, so it's a little bit less than 180. Regardless, there's a few questions to practice, but really we're dealing with angles and radians, coterminal angles, arc length, and simply getting really, really good at eventually needing to know those. Might even be worth your time to see if you can count a full rotation by 30 in radians, count a full rotation in radians and degrees using the 45-degree triangles. That is sort of it for 4.1. Remember that if you wanted to see these notes again because you were dazzled, please go to mrlemko.ca and you'll find them under the Math 30-1 review videos page. Enjoy.